In this segment, we're going to talk about linear regression, and we're going to derive the expression for the linear regression model. So we're going to talk about derivation. Now, what regression is all about is that you are trying to best fit some given data. So let me write this down first, and then I'll show you graphically. So basically, it is that you are given certain data points. Let's suppose x1, y1, x of 2, y sub 2, all the way up to xn, yn. So you're given, let's suppose, n data points. And what you want to be able to do is that you want to best fit a straight line to it. And that straight line, let's suppose we call it y is equal to a0 plus a1x. That's the general form of a straight line. Y is equal to a0 plus a1x, but a0 is the intercept and a1 is the slope of that straight line. So what we're trying to do is that somebody is giving us these data points, and what they want us to do is they want us to best fit a straight line to this data point, to these data points. So let's suppose somebody says, hey, this is the straight line which you are drawing. So the equation of this straight line which we have is y is equal to a0 plus a1x. And this is, let's suppose, x1 comma y1. And this is, let's suppose, some x of I comma y sub I, some ith data point, let's suppose. And basically you're drawing showing all those n data points on this graph here. And then you are trying to draw a straight line to best fit those data points. Eventually what you want to do is you want to minimize the amount of difference which you have between these observed values, which are the ones which are given to you, and what the straight line will predict. Because you want to minimize the amount of difference between, but at the same time you have the differences at several points, at all the data points. You have a difference here, you have a difference here, you got a difference here. So everywhere there's a difference between what you are observing and what you are predicting. So the cross is the one which you are predicting, and the dot is the one which you are observing. And now this data point here, or not the data point, but the predicted value at that particular point will be simply a0, it will be simply a0 plus a1 times x of I. Because that's a straight line which you are going to find, and then if you put the value of x equal to x of I, that's what you're going to get for the predicted value, and this is the observed value. So if you look at the amount of residual, that's what it's called. Some people call it error. So there's a residual at each and every data point which you have, and which will be the observed value, which is y sub I, minus the predicted value, which is the predicted value from the straight line. So you got y sub I minus a0 minus a1 x of I. That is the amount of residual which you are having at each data point. Now what you want to be able to do is you want to be able to somehow make these residual to be small everywhere. And one of the criteria used is to simply take the summation of all the errors, square it, and then you want to add all those errors, the square of all the errors, and which is called the SR sometimes, and what it's the SR stands for sum of the square of residuals. And that's what you want to try to make as small as possible, because eventually what the goal is to minimize the amount of residuals. And one of the criteria which is used is called the least squares method of finding the regression model. And least squares means that you are squaring the errors and you're trying to add all of them and you're trying to minimize them. And that's why it's called least squares regression. So that means that a summation of y sub I minus a0 minus a1 x of I squared, that's what you are getting from there. I is equal to 1 to n. So you want to minimize the summation there. Now you can understand that when somebody is telling you to do regression, you have these as the observed values, and this is what you're predicting. And the only control which you have is on these constants of the regression model. So these are called the constants of the regression model. And depending on what kind of regression model you're drawing, in this case we are doing a linear regression. So A0 and A1 are the two constant regression model. You want to be able to find those. Those are something which are in your control, and you want to control them in such a fashion that this summation, this whole summation becomes as small as possible. You cannot make it exactly to 0. If you make it exactly to 0, that means that the straight line has to go through all the data points, which is not going to be the case when you're doing regression. So you want to be able to make this as small as possible. So what that means is that we have to take derivatives with respect to a0 and a1, put those equal to 0, going back to your differential calculus class, to be able to minimize this expression here, minimize the summation here. So what I'll do is take the derivative of the sum of the square of the residuals with respect to a0, put that equal to 0, take the derivative of SR with respect to a1 and put that equal to 0. So that's what I'll have to do. And once I put those equal to 0, I'll get two equations and two unknowns. And once I get two equations, two unknowns, I'll be able to find what a0 and a1 are. So in order to be able to do that, I will have to take the derivative of this SR with respect to a0. So del SR with respect to a0 will be equal to summation 2 times y sub I minus a0 minus a1 x of I times minus 1 equal to 0. We are simply using the chain rule, so it's 2 times whatever is in the brackets multiplied by the derivative of this expression with respect to a0, it will be just minus 1. And then del SR divided by, with respect to a1, summation I is equal to 1 to n. Summation I is equal to 1 to n. So it will be 2 times y sub I minus a0 minus a1 x of I times the derivative of this particular quantity here, which will be minus x of I equal to 0. Because what you are doing is that you are finding out what the derivative of this quantity in the bracket is with respect to a1, and that will be just minus x of I. So we have set up two equations, two unknowns, so we need to be able to figure it out how we're going to solve these. So let's suppose if I call this 1 and we call this to be 2. So 1, what does it give me? It gives me, let me just expand this summation separately. I'll get minus 2 summation y sub I is equal to 1 to n, plus 2 summation a0 I is equal to 1 to n, plus 2 summation a1 x of I equal to 0. That's what I get from the first equation. Now what do I get from the second equation? Second equation again, I get minus 2 summation I is equal to 1 to n xi times y sub I, because I have y sub I here and x sub I here, so that's why I get that. Then plus 2 summation a0 x of I plus 2 summation I is equal to 1 to n. I'll get a1 times x of I square, because I'll have x of I here, x of I here, and that's what I'll get from there. Now I can see that 2 is common in here, so I can get rid of 2 here. I can divide both sides by 2. That's what I'm doing. I'm going to divide both sides by 2. And now since I see that here, this is a known quantity here, and this is also a known quantity here. But a0 and a1 are not, so a1 is right here. a0 and a1 are not known. a0 is not known here, a1 is not known there, a0 is not known there, a1 is there. So I'm going to keep those on the left-hand side of my equations, and this I will transfer to the right-hand side of the equations. So what I will get from there will be, the first equation will turn out to be I is equal to 1 to n a0. Then the second equation will turn out to be I is equal to 1 to n a1 x of I equal to 0. And the second equation, so that's my first equation. The second, not 0, will be summation of y sub I. The second equation will be summation I is equal to 1 to n a0 x of I plus summation I is equal to 1 to n a1 x of I square equal to summation I is equal to 1 to n xi y sub I. So again, now I got to realize that a0 and a1 are now constants, because I have found those by taking the derivative of the sum of the square of residuals with respect to a0 and a1. So I can take those out, and you can realize, what is this? This is adding a0 n times, because you're doing a0 plus a0 plus a0 plus a0. So you're going to get simply this to be n times a0. So the first equation again can be written as n times a0 plus, I can take the a1 outside. I can take this a1 outside because it's a constant, so I can take a1 outside. So I'm going to write it like that. And then summation I is equal to 1 to n y sub I. Then again here I can take a0 outside, so I'm going to take a0 outside. I get that. And then again a1 can be taken outside because it's a constant now. I is equal to 1 to n x sub I squared. And then summation I is equal to 1 to n xi y sub I. So basically I have two equations, two unknowns now, and I'm going to write them in the matrix form so that it is clear what the coefficient matrix is, what the unknowns are, and what the right hand side vector is. And also it will help you to symbolically solve these two equations, two unknowns, whether you're going to use Cramer's rule or whether you're going to use any kind of Gaussian elimination symbolically. So all of those things can be done. Or you can just use your high school algebra to solve these two equations, two unknowns. In many of the books, you will find out that many people drop this summation, these limits of summation from their books. The reason why they do that is because all the summations are the same so far as the limits are concerned. But I try to keep them because I don't want you to lose focus of that. This is, if let's suppose you're looking at this quantity, that this is a summation of the x of i's, all the x of i's are being added together. That's what that stands for. So I do keep the summations, but if you are looking at a book, please don't think that I'm doing something different. I'm just doing something which is more complete, showing you all the limits of the summations. So once you solve these two equations, two unknowns, which are written in the matrix form, this is what you're going to get. You're going to get a1 is equal to n times summation I is equal to 1 to n x of I y sub I, where n is simply the number of data points that you have. Summation I is equal to 1 to n x of I, summation I is equal to 1 to n y sub I. And then you're going to divide by n times summation x of I square, I is equal to 1 to n, minus summation x of I is equal to 1 to n square. And then a0 will be, you will get it to be summation y sub I is equal to 1 to n divided by n, minus a1 summation I is equal to 1 to n x of I divided by n. So once you have found a1, you can find a0 by simply by this simple formula here. But what is this? This is nothing but the average value of the y's. So you get y bar minus a1, and this is nothing but the average value of the x's. You get x bar. So that's how you'll be able to find a0 and a1 by doing linear regression. Now, one of the things which you got to understand where people make a lot of mistakes is this and this. If you look at this expression where you are summing the square of the numbers, square of the x values, and here where you are squaring the summation of the x values. So these two are two different quantities. This is where you have to square each x value first and then add them all up. This one is where you add all the values of x, and whatever you get as a summation, then you square it. So that's something to be thought about when you are applying these formulas to develop the linear regression formula of y is equal to a0 plus a1x. And that's the end of this segment.